The typical American household spends around $2,000 a year on energy. Heating and cooling consume more than half of that, roughly $1,000 to $1,300 annually, just to maintain a comfortable indoor temperature. Over a 30-year mortgage, that totals $30,000 to $40,000. This does not include the HVAC system itself, which costs $10,000 to $20,000 installed and needs replacement at least twice during the life of the house. All told, conditioning air can easily exceed $60,000. Every solution in this guide costs under $20, some even nothing at all, and collectively they can handle a third or more of the same work your HVAC system performs, without electricity, moving parts, or a service contract. Not every method works in every home. Some require attic access, some are ideal only for hot climates, and some are perfect for renters. By the end, recommendations will be given based on whether your climate is mostly hot, mostly cold, or a mix, and whether you own or rent. Curtains by themselves do very little. The Department of Energy found that a standard curtain on a rod reduces heat loss through the window behind it by about 10%, barely noticeable on a bill. However, sealing the same curtain to the frame with adhesive Velcro along both sides and adding a dollar store emergency blanket behind it can reduce heat loss by 25 to 38%. Researcher Baker, working for Historic Scotland, tested this on buildings with original single-glazed sash windows during Scottish winters. The key was the seal, not the fabric or curtain price. When a curtain hangs loose, warm air circulates behind it, rises over the rod, hits the cold glass, then drops and spills along the floor as a draft. This convection loop continuously pulls heat from your room to the coldest surface. Sealing the edges stops the loop. Attach adhesive-backed Velcro strips along both sides of the window frame. Stick one side to the frame and the other to the curtain edge. A board or fabric valance across the top blocks airflow over the rod, letting the air behind the curtain go still. Still air is one of the best insulators on earth. Add a mylar sheet from a dollar store behind the curtain with binder clips or safety pins, leaving an air gap of 1 to 2 inches between the sheet and the glass. This creates a poor man's triple pane window. Velcro costs $5, the mylar sheet $1, while a real triple pane window costs $600 to $1,500 installed. Another no-cost tip: in winter, open curtains during sunny days to capture solar heat, then close and seal them at sunset. Reverse this in summer. In cold climates, daytime opening also prevents condensation on the glass. The same curtains, just a change in habit. Attics are another key area. On a summer afternoon, your attic can reach 150 to 160 degrees Fahrenheit, while outside it is 95 degrees. That extra heat pushes through the ceiling into every room your air conditioner is trying to maintain at 72 degrees. In winter, warm air rises through gaps into the attic and is lost. The fix already exists in most American homes, but often doesn't work. New roof owners should note that major shingle manufacturers like GAF and Owens Corning require adequate attic ventilation for warranty coverage. If soffits are blocked, the warranty could have been void from day one. The solution costs nothing. On a cool morning, wear gloves and a dust mask if handling fiberglass. Check the eaves. If daylight shines through soffit vents, air is flowing. If insulation blocks the gap, pull it back 6 to 12 inches to clear the path. Work along the perimeter. You will feel air moving as you clear each bay. To prevent drift, install rafter baffles, foam or plastic channels holding the air path open. They look like long, shallow trays and can be stapled near each rafter. $1 to $2 each, $30 to $40 for a typical house. A homeowner in Austin balanced their system and dropped attic temperature from 140 to 95 degrees, a 45-degree reduction from an already existing air path. On the windows, another approach works directly on the glass, whether curtains are open or closed. Solar control window film, a microscopically thin filter of ceramic or metallic nanoparticles on polyester thinner than paper, blocks up to 80% of solar heat and 99% of ultraviolet radiation. The energy consulting firm Consol tested this across 4 Florida climate zones and found it 2 to 4 times more cost-effective at saving energy than upgrading ceiling insulation. A federal test at the Goodfellow Federal Center in St. Louis, analyzed by Lawrence Berkeley National Laboratory, showed films reducing HVAC energy use by up to 29%. Payback occurs in 3 years, compared with 20 to 30 years for replacement windows. Application is simple. Spray the glass with soapy water, lay the film on wet glass, squeegee bubbles from center to edge, trim excess with a utility knife, about 20 minutes per window. It lasts 15 to 20 years, and if disliked, it peels off with a heat gun. DIY film costs $5 to $15 per window. For a 10-window house, that is $50 to $150. In cold climates, standard solar film blocks heat year-round, working against you in winter on south-facing windows where solar heat is beneficial. The solution is low emissivity film, reflecting heat back toward the warmer side. It blocks summer heat while retaining winter warmth. Same application, both seasons covered, or simply film east and west windows and leave the south side exposed. A final tip takes 15 seconds and costs nothing. Most ceiling fans have a small switch on the motor housing near the blades. In summer, ceiling fan blades spin counterclockwise, pushing air down and creating a wind chill effect that makes you feel cooler. In winter, that same breeze can make you feel colder, so most people turn the fan off until June. Flip the switch and the blades rotate clockwise. Run the fan on low speed. High speed creates a draft and defeats the purpose. At low speed, the fan pulls air upward and pushes warm air pooling at the ceiling down along the walls into the room. The Department of Energy says this allows you to lower the thermostat by about 4 degrees without losing comfort, saving up to 15% in heating. An Australian consumer testing lab confirmed that a heater with a reversed ceiling fan used less than half the power of the heater alone to maintain the same temperature. The fan itself draws about as much electricity as a light bulb. The warm air was already there, just in the wrong place. Next is one of the most dramatic results. Homeowner David Mundy had a 1,300 square foot dark shingled roof. He bought 2 bags of hydrated lime from the concrete aisle of his hardware store, $14 total. He mixed it with water and rolled it onto his roof in one afternoon. Before the coating, his attic reached 140 degrees Fahrenheit on a summer day. After, it dropped to 100 degrees, a 40-degree reduction. His air conditioning barely cycled all summer. He published the data on Build It Solar. Common to every Mediterranean civilization figured this out independently. Santorini, Mykonos, and Eleusis used white surfaces as cooling systems. Lime reflects sunlight with no compressor and no electricity. Hashem Akbari at Lawrence Berkeley National Laboratory spent 30 years measuring this across hundreds of real buildings. A home in Sacramento saw an 80% reduction in daily air conditioning electricity use after a white coating. Schools in Florida recorded 25 to 35% reductions, published and peer-reviewed. For a more durable option, a white elasto roof coating costs $60 to $120 for a 5-gallon bucket and lasts years. The $14 lime wash works, but may need reapplication after a season or two. Both work best on flat or low-slope roofs, and in cold climates, a white roof reflects winter sun too. If winters are harsh and summers mild, this may not be ideal. Some homeowners associations limit roof colors to earth tones that absorb the most solar energy. In that case, interior fixes on this list become more important. A 1/8 inch gap under an exterior door causes the same heat loss as a 3-inch hole drilled through a wall, according to the National Institute of Standards and Technology. On a windy day, hold your hand near the edges of exterior doors along the sides, top, and bottom. If cool air pushes through, conditioned air is escaping. The solution is adhesive-backed foam weather stripping, costing $3 to $8 per roll. Open the door, clean the frame where the door closes, peel the tape backing, and press it along the inside of the frame on both sides and the top. Install a door sweep at the bottom, a flat strip with a rubber edge that screws to the door, costing $5 to $15. The cold spot near the front door in January could be traced to a $5 strip of foam. Inside, the average American home leaks 22% of heated and cooled air through ductwork seams. For standard pump gasoline, the target is approximately 100 to 150 degrees Celsius, depending on the blend. Diesel requires more heat, near 200 degrees Celsius. Engine coolant provides the ideal temperature for vaporizing gasoline, while exhaust pipes provide heat for diesel. Placement depends on the vehicle, but generally mount the heat exchanger near the engine block where coolant or exhaust is accessible. Install it after the fuel pump so the system remains pressurized until the heat converts the fuel into vapor. Once vaporized, it flows naturally into the intake via vacuum pressure. Modern builders have a major advantage over Pogue's 1935 design: inexpensive electronic controls. Pogue relied on passive exhaust heat, causing temperature swings based on engine load. Idling cooled the exhaust, preventing full vaporization, while highway speeds risked vapor lock. Today, thermostatic valves or digital sensors control small electric coolant pumps, maintaining a consistent vaporization temperature under all conditions. A digital sensor monitors the fuel line, adjusting hot liquid flow to keep the temperature constant, eliminating vapor lock, ensuring smooth operation, and maximizing fuel economy. Electronic controls make modern setups far safer, easier to install, and more reliable than mechanical rigs from the 1930s. There is one more piece, deliberately hidden: a vapor recirculation method that increases efficiency by an additional 30%. General Motors engineers documented it in a 1968 SAE technical paper. The principle is simple: capture unburned fuel vapors from the engine's crankcase ventilation system and route them back into the intake manifold alongside fresh, vaporized fuel. Normally, engines vent this fuel into the atmosphere or burn it inefficiently through the PCV valve. That vapor represents fuel that escaped past the piston rings during compression. By recapturing and reburning it, you reclaim energy that would otherwise be lost. GM engineers calculated that combining this with a thermal vaporizer could exceed 300 miles per gallon under optimized test conditions. This was published in June 1968 as SAPEL Document 6-80457. The paper was presented, archived, and never implemented in factory vehicles. The method is fully detailed in Section 4, pages 9 to 12. Replicating it requires one extra vacuum line, a basic check valve, and a port on your intake manifold. Parts cost under $20, and efficiency gains are measurable on the first tank of fuel. Combine a thermal vaporizer using engine coolant, managed with a digital temperature sensor and crankcase vapor recirculation, and your system can achieve 150 miles per gallon in normal driving. This is not theory, it is documented reality, proven by mechanics and engineers, deliberately buried for nearly a century. At 150 miles per gallon, a standard 15-gallon tank covers over 2,000 miles. With gasoline around $350 per gallon, refueling occurs roughly once every 2 months. A $4,000 annual fuel budget drops to under $300, keeping $3,700 in your pocket instead of giving it to oil companies. If every American driver saved similarly, the petroleum industry would lose hundreds of billions annually. That is why this technology was buried. That is why Charles Pogue signed an NDA. That is why Tom Ogle died before finalizing a contract. And that is why thermal fuel vaporization remained unknown until now. Your grandfather may have had the blueprints to eliminate his gas bill in his shed. He did not build it because powerful interests prevented him. His $6 setup in 1935 could have saved tens of thousands over a lifetime. Today, a $60 weekend project can do the same for you. This demonstrates the difference between buying a consumable product and building a permanent solution. Corporations profiting from your fuel dependency have kept this hidden for 90 years. True independence is not avoiding modern cars. It is refusing to accept massive fuel bills as unavoidable. Navy logs, SAE papers, and suppressed patents prove it. This is not conspiracy. It is documented structural suppression. Pogue's patent is public. Navy logs are in the National Archives. Ogle's death certificate is public. The GM paper is in the Sapple Library. The evidence is not hidden, just ignored. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.